This is Professor Erling Dorf, Department of Geology, Princeton University. His subject today, climates of the past. The National Broadcasting Company, in cooperation with Princeton University, presents Princeton 55, an exploration into education through television. A series of programs intended to bring into your living room the exciting ideas and important men of one of the nation's leading universities. Princeton 55 is intended for the listener with an inquisitive mind. Now meet Professor Erling Dorf. His subject, climates of the past.
Good afternoon. The phrase climates of the past perhaps brings to many of your minds the recollections of the climate of your own past. The good old days when the winters were much colder and the snow seemed much deeper than they are nowadays. From that point of view, that is a short-range point of view, the present climate is unusually warm, despite, of course, occasional cold snaps. In terms of the geologic past, however, our present climate is unusually cold. In fact, we're living in a glacial age when we compare the present to the good old days of the really distant past, say 40 or 60 or even 100 million years ago. Let's see if we can illustrate this by means of a chart. Here we see, for example, and this represents the geologic time back to about 500 million years ago, that beginning with an unknown portion back in the too far distant past for us to be certain of, there seems to have been a cold glacial climate followed by a warming of the climate to a normally fairly warm climate ranging from 20 to 30 degrees warmer than the episode when there was the cold glacial climates. This warmer episode lasted for, as you see, many millions of years, and then there was a second glacial episode when the temperatures dropped 15, 20, or 30 degrees and produced another glacial episode, resulting in the development of ice sheets throughout much of the southern hemisphere. After that, the climate warmed again, and we have the considerably warmer spell lasting again for several 100 million years to about a period roughly 60 to 70 million years ago, when, with some minor fluctuations, which you see here, there has been a general trend from the normally warmer climates of geologic time to the what we might call glacial climate of today. Now, we might say then that we are in a minor warm spell within a major cold spell. What I should like to demonstrate this afternoon is how we try to learn about past climates. The geologist is concerned with a great many reconstructions of past conditions. We'll concentrate on past climates and try to illustrate how the geologist tries to work on climates of the past. First of all, we must realize, of course, that there is no such thing as a fossil climate. We must rely on other lines of evidence. Let's begin at the beginning. The geologist relies, first of all, on the principle that the present is the key to the past. In other words, if we can find something, perhaps something living, as we'll see, in the present conditions of the world, they can help us in depicting the climates of the past. We find actually that the distribution of plants is very much the same as the distribution of climatic zones. The plants are more sensitive than are the animals to climatic changes. And so, for example, we find there are no palms or figs or breadfruit trees growing in Central Park, New York, simply because the climate in that region is too cold. That is, specifically, the winters are too cold. And we find, as we think of it, that the tundra of the north is characterized by reindeer moss and lichens with virtually no trees except a little dwarf willow and an Arctic birch. This is a polar climate. And the cold temperate climate south of the polar climate is characterized by such things as the spruces, the larches, the firs, the hemlocks, a few birches and alders among the hardwood trees. And so for most of our climatic zones, we can think of and we can find different types of vegetation which are particularly characteristic of that specific climatic zone. By this token, we can therefore use fossil plants, those that we find in the rocks, as indications of our climates of the past. Let's look at a few examples. Here, for example, is a rather perfectly preserved palm leaf, as I'm sure you can all recognize. It comes from a deposit in southeastern Wyoming, actually an old lake deposit. This material was originally mud which settled to the bottom of a lake, and this, of course, was originally a palm leaf which came from a palm tree, drifted out into the lake, and subsequently sank and became buried in the mud at the bottom of the lake. Now, of course, a palm, if we are to use the present conditions as a help to depicting conditions of the past, a palm is indicative of tropical or subtropical conditions, quite different from those which we find in southwestern Wyoming today. If we look at another type of leaf, here, for example, this is a member of the fig family. You may not recognize it unless you have spent some time in the tropics. This, too, comes from the same ancient lake deposit of southwestern Wyoming. And it, too, because we know it's a fig, and the figs are distributed today only in tropical and subtropical conditions, we know, therefore, that it, too, like the palm, points to subtropical and tropical conditions in Wyoming back 45 million years ago, when these left their imprints in the rock. We can say, in other words, that the change has been quite remarkable from the past to the present. Here is a view of the area, the actual cliff, as a matter of fact, where these fossil leaves were obtained. It's a desert region with only about 5 to 10 inches of rainfall at a high elevation, and of course the entire assemblage of plants from this region, like the palm, like the fig that I've shown you, indicate conditions quite different and would be illustrated by conditions such as these, for example. Subtropical conditions with beautiful palms, hardwood figs, other subtropical trees in the general vicinity. Now, if we turn to a second type of indicator, here we have, for example, a grouping of fossil maple leaves, as you can probably recognize. These and the accompanying maple fruit, which you can probably see there, come from the Eocene deposits of Yellowstone Park, roughly 50 million years old. These are, instead of the subtropical type, they represent temperate types of plants, the maples being distributed not under subtropical, tropical conditions, but only under the temperate conditions. Similarly, here we have some impressions. These come from central Colorado. These are about 30 million years old. These are imprints, in this case, of the twigs of a redwood, and these are the impressions of the cones of a redwood, very similar to the California redwood, which still grows in western California. And this, the almost perfect mold of one of these redwood cones preserved in the rocks. They, like the maple, indicate temperate conditions of growth. Now, on the other hand, if we look at This impression, you can probably see that it's an impression of a pine cone. Here, some of you might think that the pine would be an excellent climatic indicator for temperate conditions. But others of you, if you've been south, may think that this would be more indicative of warmer temperate to subtropical conditions. Well, here we have an example of the type of plant which we can't use as a climatic indicator. The pine is known from sea level to timberline, from the tropics to the Arctic region. It's too cosmopolitan to be used as a very good climatic indicator. This, of course, immediately raises a question. How many of these cosmopolitan kinds of plants do we have? Must we be careful that we don't have too many of them to contend with in terms of the prediction of past climatic conditions? Fortunately, we don't have many of these cosmopolitan forms. And in the long past history of vegetation, most of the different types of vegetation have pretty well stay confined to their respective climatic regions. We have a few extensions of tropical types of plants in the temperate regions, such as the magnolia and the sassafras in the eastern part of North America, but they're truly the exception rather than the rule. But nevertheless, our climatic indications based on a few plants need to be substantiated by other methods. One of the chief methods by which we check our conclusions based on climatic indicators is the study of the entire assemblage of fossil plants found in any one deposit, representing the whole forest, rather than merely a few of the components of that forest, which might not tell us the whole story. In this connection, let's illustrate that by means of a few pictures. This, for example, represents southeastern Alaska. And here in southeastern Alaska, during the Eocene, about 40 million years ago, there were deposited, and we find today in rocks of that age, very well-preserved remains of palm trees, cycads, or sago palms as they're called, magnolias, laurels, pepper plants, avocados, delenias, and other subtropical types of vegetation less familiar to us, all of which indicate a tremendous change in climatic conditions from the Eocene to the present time. Here again, in the region of western Greenland, in Disco Island, we find fossils approximately 45 million years old. In a region such as this, almost devoid of all vegetation, with a little tundra here and there, perhaps an occasional dwarf willow or Arctic birch, that's all in the way of vegetation. But here in the rocks, we find remains in the Eocene of oaks, maples, poplars, sycamores, elms, tulip trees, sweet gums, and beeches, all of which indicate to us that Greenland back in the Eocene must have supported a vegetation much like this of our Middle Atlantic states. And lastly, as an illustration, we might take the Eocene fossil plants of Cape Murchison of Grinnell Land, which lies only about 8 degrees from the North Pole, and today is a very Arctic, cold, forbidding region with only a bit of tundra here and there. Here we find fossil plants of pines and firs and hemlocks, poplars, birches, and hazel, all of which, when viewed as a total forest assemblage, is comparable to the cold, temperate forests such as those which live today in northern New England or southern Canada. And of course, again, represents a tremendous change in climatic conditions. These, then, are some of the methods which we apply in the application of fossil plants to reconstructions of past climates. There are other means. I'd like to demonstrate just one, in which we can check our results without any particular regard to the kinds of plants which are represented. If, for example, we compare the general character of these maple leaves with the general character of the fig leaf over here, we see that they're built quite differently. The fig leaf has a smooth margin, an elliptical shape. It isn't lobed such as the maple. The maple has little teeth on the margins. This general type of leaf, regardless of what group it belongs to, that is the type which has a toothed margin, is very typical of temperate forests, and this type of leaf is very typical of subtropical and tropical forests. So in any assemblage of fossils, we can get a very good idea just from the relative proportions of this type of leaf and this type of leaf, what general type of climatic condition is represented. Now, we are, of course, anxious in all reconstructions to substantiate our results with other types of fossil remains, such as these. Here, for example, is a petrified head of an alligator. This comes from the Eocene of Wyoming, and it, like the palms and the figs, represent subtropical to tropical conditions and verifies the conclusions based on fossil plants. Quite a different sort of fossil remains is this. This is the horn of a musk ox. It comes from New Jersey. It's not more than a few million years old. And it, of course, since the present musk ox is restricted to rather tundra conditions, very cold Arctic conditions, must mean that New Jersey, back a few million years ago, was considerably colder, not warmer, than it is at the present time. We get the same result from these. These are tusks, walrus tusks, which again come from off the coast of New Jersey, and they, since the modern walrus is restricted to Arctic waters, indicate a time in the not too far distant past when New Jersey was much colder than it is at the present time. And then lastly, as an illustration of the kind of climatic indicators we get among those animals which live underwater, here is a reef coral. This reef coral comes from northern Europe. It's about 280 million years old. We know that reef corals today live only in the warm, clear waters of the subtropical and tropical seas, and this, like the others, show a considerable change in climatic conditions since it lived in the warm seas of northern Europe. Now, beyond the general work of working with fossil animals and plants, there are many other interesting lines of endeavor which have led to conclusions respecting climates of the past. One of the more interesting ones developed rather recently is the study of oxygen isotopes in seashells. It so happens that the two isotopes of oxygen, oxygen-16 and oxygen-18, occur together in the proportion of 1 part oxygen-18 to about 500 parts oxygen-16 under normal conditions. But this proportion varies according to the temperature of the water in which the shells grow. And consequently, we can take ancient shells and determine the ratio of oxygen-16 to oxygen-18 and get some idea of not only the temperature, but the temperature changes which have occurred in the geologic past. I should also mention that in terms of geologic climates, sometimes the geologic deposits themselves are extremely helpful to us. For example, the most obvious, if we recognize in a region glacial deposits, and they're not too difficult to recognize, obviously this indicates a glacial climate, a time when the ice covered a particular region. Recently, the study of soils and of sediments which occur in our rocks leads to climatic conclusions. The red soils, for example, being rather typical of humid tropical and subtropical conditions. Now, so much for our methods. Let's see to some extent, and only tentatively, because all of our results are tentative. We're continuing to build up our pictures, but let's see what some of our results have been based on the kind of methods which I've tried to demonstrate. If, for example, we look first of all at our present climatic conditions based on modern vegetation, we see here that there is, beginning with the subarctic tundra region, the cold temperate conifer forests, below which there occur the warm temperate, mainly hardwood forests, though there are some grassy plains, of course, out in here, and deserts in the southwest, and below that, the general distribution of the subtropical and tropical vegetation. These are illustrative of the zones. Now, if we move back 40 million years ago to the Eocene, the first thing we notice is that the outlines of North America are quite different. There's no Florida. Florida was completely covered by water, and the Gulf of Mexico extended up into the interior as far as our present southern Illinois. And here we see, and we think we know from the distribution of various fossil plant localities here and there throughout the west, and to some extent the east, that the subtropical vegetation occupied a region much farther north than we find it at the present time. And the tropical type of vegetation extended up into our present Gulf region. Now, if we jump from the late Eocene to the late Oligocene, roughly 30 million years ago, here we find that the different zones of vegetation have been shifted southward. They have migrated, so to speak. The forests have migrated as a result of the climatic changes. The subtropical belt has been pushed farther south. The warm temperate and cold temperate zones have expanded. Now, if we move still farther along to the mid-Miocene, about 18 million years ago, here we find a slight reversal of climatic trend. The subtropical types of plants have moved upward again. And this belt, differentiating the subtropical from the warm temperate, has moved its position in contrast to its position in the former slide. Now, if we go still farther along into the late Pliocene time, about 3 million years ago, here we see that apparently from our study of the fossils here and there and elsewhere, that the conditions, the climatic conditions, are very much as we find them today. That is, the warm temperate, cold temperate, subtropical zones, as indicated by the vegetation that we find in the fossils, is very similar to that of today. However, as we'll see in the next slide, the glacial episode intervenes. And we have, beginning about 960,000 years ago, a time when the ice developed over much of the northern part of the North American continent, extending down into our own northern states, which of course in effect obliterated the vegetation underneath it. But south of the glacial margin, it shifted the different belts of vegetation southward to the position shown on this chart. We know, for example, that there were conifers of the cold temperate type, spruces, firs, the Canadian larch as far south as Louisiana and northern Florida. And we find, for example, that there were remains of the walrus along the Atlantic coast, all the way from New Jersey down to South Carolina and Georgia. We find, for example, that there were remains of the musk oxen south as far as central California, others in New Mexico, Mississippi, and other parts far south of their present distribution. We find moose, typical of cold temperate region, extending as far as latitude 40 down to about this general line, all of which indicate a shifting of climatic zones far south of the previous Pliocene epoch. Now actually, there were 4 such invasions of the North American continent by ice sheets, but for the sake of time, we'll illustrate only one interglacial episode in which the vegetation seems, at least during one of the interglacial episodes, to have produced a distribution of climatic zones such as this, in which the warm-temperate, cold-temperate boundary is somewhat farther north than we find it actually at the present time. In other words, one of our interglacial episodes, at least, was warmer than the conditions that we find on the North American continent today. Now let's show in the last picture of the glacial age the change from this interglacial period to another ice age. We need not go into further details about this because we've already indicated the effect of the ice sheet and the cooling climate on the distribution of the forests south of that border. And from that time to the present time, there has been a gradual warming of the climate with the various types of forests following in the wake of the retreating glaciers and occupying the positions indicated here. Now the last million years shows this very interesting series of changes in climatic conditions. We had actually, rather than 2 glacial episodes that I showed, we had 4 different glacial episodes as a result of fluctuations toward colder and colder conditions with interglacial episodes in between, ending up in the last 10,000 years with this trend toward warmer conditions and again a cooling off of conditions here with slight fluctuations from time to time. These minor fluctuations are, of course, quite common, and perhaps there were other minor fluctuations here which we yet don't know too much about. Now, as to the causes of these climatic changes, I wish there were time to go into something in the nature of that. I think all we need to say is that a combination of changes in the sun's heat energy and the elevation of continents seems to be the most favored hypothesis at the present time. You might want to know, what about the future? Well, as a geologist, perhaps I shouldn't say anything about the future. I'm a student of the past. But at least we can say this, that we can be certain that there will be fluctuations in climate. It's a little bit like trying to predict what the stock market's going to do. The climate, I think, is going to have its ups and downs, but we can't tell where and when it's going to shift from colder to warmer. We may be in for another gradual cooling and a glacial advance in the next 100,000 years and have white Christmases lasting all year. Or if our warm spell continues, we may end up 100,000 years from now with palm trees and alligators in southern New England and the Jersey Shore, a winter resort for the farmers and industrialists of Greenland. Thank you. Good afternoon.
This has been Princeton 55, an exploration into education through television. Featured today was Professor Erling Dorf. Next week at the same time, Princeton 55 will present Professor Louis V. Thomas, Department of Oriental Languages and Literature. His subject, the Near East. Vic Roby speaking. This has been a WRCA.